Today we'll be talking about the integral test. The integral test looks at a function, and if the function is a continuous, positive, and decreasing function from 1 to infinity, and we let a series equal fn, then this series is convergent if and only if the improper integral is also convergent. In other words, if the integral is convergent, then the series is convergent. And if the integral is divergent, then the series is also divergent. Let's practice this. Determine whether the series from 1 to infinity of 1 over n squared converges or diverges using the integral test. Our first step should be seeing if this series meets the conditions for the integral test. Looking at this function, we can tell that this series is continuous for all values greater than 1. It is also positive for all values greater than 1. To determine if the series is decreasing for all values greater than 1, we'll take a look at the first derivative. After taking the first derivative, we determine that it is equal to negative 2 over x cubed. We substitute x for a value greater than 1, and in this case we put 2, and this equates to negative 2 over 8. Because this value is negative, we know that this function is decreasing for all values greater than 1. Now that we know all these conditions are met, let's determine if the series converges or diverges. We'll look at the integral, and we'll solve the integral from 1 to infinity. After solving the integral, we see that it's negative 1 over x plus 1. Negative 1 over x approaches 0 as x gets larger, so that equals 0. So our final answer for this integral is that it equals 1. Because 1 is a finite number, this integral converges. Based off of the integral test, because the integral converges, this series also converges. Let's do another practice problem. For this problem, we'll determine whether this series converges or diverges using the integral test. To redefine the function, we'll redefine it as fx equals 1 over x times the natural log of x. First step here again, we'll determine if all the conditions for the integral test are met. All the conditions are met for the integral test. So let's start solving for the improper integral. Using u substitution, our final integral is the natural log times the natural log of x from x equals 2 to x equals infinity. Here, natural log times the natural log of b as b approaches infinity is equal to infinity minus the natural log times the natural log of 2. Here, because the limit does not approach a finite number and instead approaches infinity, the integral also approaches infinity and diverges. Based off of the integral test, because the integral diverges, this means the series also diverges. We'll now look at another method to see if a series converges or diverges. We'll be looking at the comparison test. Suppose that we have two series, an and bn, with positive terms. If bn, our series, is convergent, and an is less than or equal to bn for all n, then an, the series, is also convergent. If the series bn is divergent for all n, an is greater than or equal to bn, then our series an is also divergent. Let's take a look at an example to see what this means. Here, we'll determine whether this series converges or diverges using the comparison test. We'll first want to find a suitable comparison series. We'll be using something called a p-series. Looking at our original series, 1 over n cubed plus n is pretty close to 1 over n cubed. This is what we call a p-series. A p-series is the summation of 1 over n to the p power. It also converges if p is greater than 1, but it diverges if p is less than or equal to 1. Our p-series is 1 over n cubed. Because p here is equal to 3 and 3 is greater than 1, we know that our p-series converges. Going off of the comparison test, because our original series 1 over n cubed plus n is less than or equal to 1 over n cubed for all values of n greater than 1, and because the p-series converges, this means that our original series 1 over n cubed plus n is also convergent by the comparison test. Let's look at another practice problem. For this problem, we'll determine whether this series converges or diverges using the same comparison test. To solve this question, we'll need to look and find a suitable p-series that we can compare this original series to. For a large value of n times n plus 1 is pretty close to n squared. So our original series is pretty similar to 1 over n squared. In this case, 1 over n squared is our p-series, where p is equal to 2. Because 2 is greater than 1, this new series here converges. Keeping that in mind, when we compare our original series to 1 over n squared, our p-series, we know that our original series is smaller or equal to our new p-series 1 over n squared for all values of n greater than or equal to 1. Because this series 1 over n squared converges, by the comparison test, our original series also converges.